Welcome to another deep dive. And today we're tackling something that might sound a little complex at first, but it's actually all around us. Time series analysis.
Yeah, that's right. We'll be uncovering those hidden patterns and trends in data that changes over time. And guess what? That's pretty much like, well, everything.
Exactly. Buckle up, because we're going to break it down so anyone can understand the basics.
You don't need a fancy degree or anything like that. Think about something like the stock market.
Oh yeah, good one. Every day those prices are going up, they're going down, they're all over the place.
See? Time series.
So that means like temperatures, fluctuating throughout the day and across the seasons.
Another perfect example of a time series.
So basically, anytime we're tracking something over time, like even something as simple as how many cups of coffee we drink every day,
That's right.
that's a time series. And with the right tools, we can start to make sense of all those changes.
We can, and maybe even predict what's going to happen next.
Now, before we get too deep into the weeds, there's this fundamental concept, right? I think it's called stationarity.
You got it. Stationarity. It's really important because a lot of time series models rely on the assumption that the data is stationary.
Which basically means...
It means that its statistical properties remain constant over time.
Okay, wait. Statistical properties. That sounds a little intimidating. Can you break that down for us?
Of course. Imagine a coin toss. So in a truly fair coin toss, the chances of getting heads or tails, they stay the same, right? Flip after flip.
Yeah, that makes sense.
So that is an example of strict stationarity. The statistical properties, in this case the probability of each outcome, heads or tails, they remain constant over time, no matter how many times you flip that coin.
Okay, that makes sense. But I'm guessing that things in the real world are rarely that perfect.
Right. What about those stock prices we were talking about, or the temperatures?
You're absolutely right. They're constantly fluctuating. And strict stationarity, it's often too strict a condition for that messy real-world data. So that's where this idea of weak stationarity comes in.
Exactly. Weak stationarity is much more flexible. Instead of requiring all those statistical properties to remain constant, it focuses on just the mean and the variance.
Okay, so with weak stationarity, we're basically saying that, okay, the data points themselves, they can jump around all they want, but the average value and the spread of the data around that average, those have to stay relatively consistent over time.
You got it. Precisely. And in most practical applications of time series analysis, that weak stationarity is all we really need.
Got it.
It's like saying, okay, the stock price might be all over the place, but we can still analyze it if the average price and the typical range of fluctuations, those stay roughly the same.
Okay, that makes sense. Now let's dive into those building blocks you mentioned earlier.
You mean the AR and MA process?
Yeah, AR and MA processes. They kind of sound like something out of a science fiction movie.
They might sound a little fancy, but honestly, they're pretty intuitive once you get to know them. The AR process, which stands for autoregressive process, tells us that the current value in a time series depends on its own past values.
Okay, so it's like saying today's stock price is influenced by what the stock price was yesterday, the day before, and so on.
Exactly. And the P in ARP, that tells us how many past values we're considering.
So an AR3 process would mean that the current value depends on the values from the 3 previous time periods.
Exactly. You can think of it as the data having a memory, where those past events still echo into the present.
Interesting. Okay, so I'm starting to see a little bit of a pattern here. What about that MA process? How is that different?
The MA process, or moving average process, it's a bit different. It says that the current value is actually influenced by past error terms.
Okay, now these error terms, this might sound kind of technical, but could we think about them as like surprises or unpredictable fluctuations that happened in the past?
You got it. It's a great way to think about it. So instead of looking directly at those past values like we do in that AR process, the MA process focuses on how past surprises or deviations from expectations are still impacting the present.
Got it. Okay, so the Q in MAQ would tell us how many past error terms we're considering. So an MA2 process, for example, means that the current value is being influenced by the surprises from those 2 previous time periods.
Exactly.
Wow, this is really fascinating. So we have AR looking at past values and MA focusing on past surprises. But how do we actually figure out which of these processes is at play in a given time series? Like, how do we decode all those patterns hidden in the data?
Well, that's where our detective tools come in. The ACF and PACF,
Okay.
they give us a really cool visual way to see those echoes from the past and pinpoint whether we're dealing with an AR process, an MA process, or even a combination of the two.
Okay, I'm ready to unleash my inner data detective. Tell me, what are these tools all about? What are the ACF and the PACF?
All right, well, let's start with the ACF. That stands for Autocorrelation Function. And it's essentially a measure of how much a data point at a particular time is correlated with its past values. Like, think of it like looking for echoes of the past in our data.
Okay, so if we were looking at like daily stock prices,
Yeah.
the ACF would tell us how much today's price is related to yesterday's price, the price 2 days ago, and so on.
Exactly. And what's really cool about the ACF is that it doesn't just give us a single number, it gives us a whole series of correlation values for different time lags. So we can see how this relationship between those prices, how it changes as we go further back in time.
So it's like we're creating a map of how much the past is influencing the present, but at all these different time intervals. I'm already imagining some cool visual.
You got it. And you know those source materials you shared?
Yeah.
They actually have some great visual representations of the ACF. Those plots with the bars showing the correlation at each lag, it really helps to see the pattern.
That's awesome. So let's say we're looking at an ACF plot, and we see that the bars are gradually, decreasing in height as that lag increases. What would that tell us about our time series?
Well, that's a pretty common pattern, and it basically suggests that the correlation between those data points, it weakens as they get further apart in time. It's like saying the influence of the past fades gradually, which makes sense, right?
Right, yeah. But what if we see something different? What if we see like a sharp drop in the ACF
Yeah.
after a specific number of lags?
That's when things get really interesting and our detective skills really come into play.
Okay.
Because a sharp cutoff in the ACF, that's often a telltale sign of a moving average or MA process at work.
Oh, right.
Remember how that MA process, how it's all about those past surprises or error terms?
Yeah.
Well, if the ACF suddenly drops to 0 after, say, 2 lags, it suggests that only those past 2 error terms, those are the ones significantly impacting the present.
So that sharp cutoff helps us pinpoint the order of the MA process, the number of past error terms that actually matter. That's a pretty neat trick.
It is. And just like the ACF helps us identify those MA processes, our other detective tool, the PACF, this one's particularly useful for spotting those autoregressive or AR processes.
Right, the PACF, or the partial autocorrelation function. Now that one, it's all about isolating the direct influence of a past value on the present. Is that right?
You nailed it. The PACF goes a step further than the ACF. It actually filters out those indirect effects that might be coming through other past values. It's like we're zooming in on the specific relationship between 2 data points, and we're removing all the noise from those other factors.
So if we were trying to understand how much yesterday's temperature directly affects today's temperature, the PACF would help us separate that effect from any indirect influence coming from the temperature 2 days ago, 3 days ago, and so on.
Exactly. And here's where it gets really interesting. Just like a sharp cutoff in the ACF points to an MA process, a sharp cutoff in the PACF, that suggests that an AR process is driving the pattern.
Okay, so let's say we see a PACF plot that drops to 0 after 3 lags. That would be a strong hint that we're dealing with an AR3 process where only the past 3 values are directly influencing the present.
Precisely. And that's the power of these tools. By examining both the ACF and PACF, we can start to make informed guesses about the underlying processes that are shaping our time series data. It's like having a decoder ring for understanding the language of time.
I'm loving this. It feels like we've gone from these like abstract concepts to these really practical tools, and it's all starting to click into place.
That's the beauty of time series analysis. It's a field that bridges that theory and application, giving us a way to make sense of all those patterns that are all around us. And you know what? We've only just scratched the surface. There's a whole universe of techniques and applications waiting to be explored out there.
This is incredibly exciting. We've uncovered so much already, from the basics of time series and stationarity to those powerful detective tools, the ACF and PACF. I can't wait to see what else we uncover as we continue this deep dive.
Well, hold on tight, because we're about to wrap things up with some key takeaways and a final thought-provoking question that'll leave you pondering the power of time series analysis in your everyday life.
Welcome back to the final part of our deep dive into time series analysis. We've learned a lot, haven't we?
We have. It's been pretty amazing.
It has. So we started with stationarity, and that's really like setting the stage for all of this, isn't it?
It is. It is. Making sure those statistical properties that we're analyzing, that they're staying consistent, that's really key for a lot of these time series models that we're talking about.
And we dove into AR and MA processes.
Say building blocks.
Yeah, the building blocks. And understanding like how those past values and those past errors are influencing the present. Super important.
For making sense of any of this data, yeah.
And then those detective tools The ACF and the PACF, those are so cool.
They are cool, and they help us to really pinpoint those patterns, right?
Yeah, and like visualize it
Visualize it, yeah.
of those AR and MA processes.
Ah. It's almost like we can see what's going on under the hood.
And not only that, but we can actually determine like the order of those processes, right?
Yeah.
You can see how many past values or errors are actually driving those patterns that we see. It's amazing.
Yeah, when you break it down like that, it's like, it's not that complex, huh?
No, it's really not. And that's what I love about this deep dive. These seemingly really complex concepts, when you break them down, they're actually pretty understandable.
They are. It's like we've gained this whole new set of lenses, like we're looking at the world through new eyes, and we can start to understand how things change over time.
Exactly. So as we wrap up this incredible deep dive, what are some key takeaways that we should leave our listeners with?
Well, I think first and foremost, time series analysis, it's all about understanding data that evolves over time. It's like the stock market or even your daily steps, the temperature outside. It's recognizing those temporal patterns. It's really key.
Right. And to really make sense of those patterns, we need to consider stationarity.
Yeah.
Right? It's like before we build anything, before we start making these models, we need to make sure that the ground is stable.
Yeah, absolutely. And once we have that foundation, then we can start exploring those building blocks, those AR and MA processes that we talked about, and really understand how those past values, those past errors are influencing the present.
Yeah, and it's all about using our trusty tools,
Hmm.
the ACF and the PACF.
They're like our time series detectives.
They are?
They're helping us uncover those hidden patterns.
Yeah, it's really cool. It's all about connecting the dots. It's like the data is telling us a story, and we just have to listen.
Yeah, and this is just the beginning. We've just touched on the basics. There's so much more to explore in the world of time series analysis.
So much more. Well, this has been an incredible journey. Thank you so much for joining us. For our listeners, if you want to learn more about this and other fascinating topics, be sure to check out AIM's Threads page at AI in Minutes. They have so much great content there.
Yeah, it's fantastic. And remember, even these really complex topics, they can be broken down and understood. You just got to have a little curiosity and be willing to put in a little effort, and anybody can start seeing these hidden patterns all around them.
You got it. So until next time, keep those data points flowing.